Quantum numbers. So we're going to use quantum numbers to describe an electron around an atom in its position where it happens to be around an atom. So Bohr's planetary model could only explain the general energy levels of the electron. So the Bohr-Rutherford models that we know, they are able to describe in general what energy level the atoms are on, but they don't go to describe any more details of those. And the calculations that Schrodinger did for his wave equations in terms of placing the electrons around the atom in terms of where they could be, the probable locations for those electrons, aren't fully described by the energy levels seen in Bohr's quantum model. So what we would have been calling orbital 1 or our shell number 1, that describes a little bit about the energy level, but not quite enough about it. So we're going to use quantum numbers. We're going to use more details to describe where the electrons are. We can think of the first of these quantum numbers, there's going to be 4 of them. We can think of the first one as being roughly analogous to the shells that we used in the Bohr-Rutherford diagram. So in shell 1, where we put 2 electrons with a Bohr-Rutherford diagram, we can sort of think of that as being representative of the first value for the first of the 4 quantum numbers. So we're going to call this first one the principal quantum number, and instead of writing that out each time, we're going to just use a little n to describe that we're talking about the first quantum number, the principal quantum number, and its values are whole numbers. So the energy level that the electron can be on could be on energy level number 1 or energy level number 2 or 3 or 4. And we know based on the wave properties of the electrons, they can only be found on those ones. They couldn't be on 1.3 or 2.7. There have to be whole number values to denote the energy level that the electrons are on. So think of this as being what we would have referred to in the Bohr-Rutherford diagram as a shell. We're now going to refer to it as the energy level, or the principal quantum number, of which it could have several values, but they're all whole numbers. So think of energy level 1 as being n equals 1. Energy level 2 would be n equals 2, and so on, and so on, and so on. So the first quantum number is like the energy level. We're going to call that the shell, and it has values that are whole numbers. And now realize we're relating this to the planetary model, which is not the same as the quantum model. So we do have some adjustments to make in terms of the level of detail of those energy levels. But principal quantum number, whole numbers, and the symbol to represent it is a lowercase n. All right. The secondary quantum number, sort of the second bit of information that we have about a location of an electron around an atom. We can say with the first quantum number what its energy level is, but there's also this bit of information that we know from the wave equations that denotes what's called its shape of the orbital that it's in, or what we call the secondary or angular quantum number. And we're going to be using a lowercase italic L to denote that. So if we have a lowercase L, so you can denote it as that. It doesn't normally show up with typing, but generally we would write it as a lowercase L. This denotes what we will refer to as the shape of the electron orbit. So again, if we're trying to describe where an electron is around a nucleus, we can say, okay, well, it's going to be most likely found in this particular area based on the calculations that Schrodinger worked through, the wave equation calculations. It's most likely to be found in this particular shape. And there are several different shapes. This is the secondary quantum number. We're referring to a shape. It has the symbol little l. Now, in terms of its values, we'll look at those in a second, but you can think of this as being sort of like the little steps within each shell. So if you go back to thinking about the Bohr-Rutherford model, we know that the first shell holds 2 electrons, the next one holds 8. But within that second shell, there's actually 2 sort of little steps within that energy level. And the secondary quantum number, the angular quantum number, will tell us which of those 2 steps we're on. So if we were on the secondary energy level, the principal quantum number would equal 2, but there could be 2 little steps within level 2. And so if we want to say which step we're on, we'd want to use this angular or secondary quantum number to say which one it is on. Now, the values for this are based on the equations. We're going to look at the rules of what the values can be, and then we're going to put it together in terms of determining what are the possible places where the electrons could be. So the values for the second quantum number are going to be based on whatever n is. It can go up to what n is minus 1, and it's going to start at 0. So however many little steps there are on each energy level is based on what you can get as possibilities between 0 up to whatever the n value is minus 1. Let's see what that would look like. So, for example, let's say the principal quantum number is 1. So if the principal quantum number is 1, then the possible values for the secondary quantum number are going to be 0 up to whatever the n value is minus 1. Now, if the n value is only 1, 1 minus 1 would be 0. So the only possible values for our second quantum number would be 0 and 0, which is just 0. But if we had n equals 2, on the second energy level, L could be 0 or it could be 1, because the values for L are based on 0 up to n minus 1, and on the secondary, on the second energy level, when n equals 2, there would be 2 different places, or think of it as 2 little steps that we could have on that second energy level. The first energy level only has 1 step on it, but the second energy level has 2 steps on it. Then, if we look at n equals 3, the possible L values go from 0, 1, and 2, because they go from 0 to whatever n value is minus 1. And in this case, n is equal to 3, so the possible L values are 0, 1, and 2. So, if n equals 4, L values would be 0, 1, 2, and 3, and so on and so on. So the rules for determining what are the possible values for the secondary quantum number, we're going to use L to denote that we're talking about the secondary quantum number, and they go from 0 to whatever n value you're talking about. So again, remember, we're using this to describe the place of an electron around a nucleus. So if the electron is on principal quantum number level 1, so if the first quantum number is equal to 1, then its options within that energy level are only 0 for its secondary quantum number. But if there's an electron on energy level 2, it could be in one of 2 places. It could be on this little step here or this little step here. And we were giving these the titles of little step 0 and little step 1. Those are the 2 possible places where that electron could be. The third quantum number is the magnetic quantum number, and this denotes the orientation. So let's just quickly go back through these 3 options. So the first quantum number, the principal quantum number, denotes the energy level. We're going to call it the shell. The second quantum number denotes the shape, and the third quantum number denotes the orientation of those subshells. And so you can think of this as sort of the direction in which the shape is pointing. So the third one, we're going to use the symbol M subscript italicized L, and so it's going to be based on what the L values are. Depending on what the L values are, there will be certain ML values, or third quantum number values. So they range from whatever the value of L is as a negative, going all the way up to whatever the values of L are as a positive, going through 0. So let's look at the options here. So when L equals 0, let's take a look back at the secondary quantum number. So when n equals 1, L could equal 0. When n equals 2, L could equal 0 or 1. So in any of the cases where L is 0, then the options for the third quantum number, the magnetic quantum number, or ML, are only 0, because negative 0, 0, and 1 are all, negative 0, 0, and positive 0 are all just 0. But let's look at the second energy level. When n equals 2, there's two values for L. It could be 0 or it could be 1. If it is 1, we'll go to the third quantum number again. If the L value is 1, then what that means is that the ML values for that particular little step or that particular shape is -1, 0, or +1. There's 3 possible ML values when you are dealing with an L value of 1. When you're dealing with an L value of 2, you have 5 possible values. It starts at whatever the L value is as a negative, going all the way up to whatever the L value is as a positive and through 0. So for every increase in L value, you have 2 more possible ML values. So that is the third quantum number. And there's a fourth quantum number, a last one, only 4. What they found with the spectral lines is they actually saw that they were influenced. Not only did they have a particular energy level with a particular shape and a particular orientation, but for every one of them, there's actually 2 distinct lines. And so there's this other property about where these electrons can be called spin, of which there's going to be only 2 possible values. So the spin quantum number, we give it the symbol ms instead of writing it out each time, m subscript s. It has 2 possible values, and we're going to call them the spin. Don't worry too much about why it is called a spin, but it is referred to as the spin of the electrons. And the 2 possible values for this fourth quantum number, or the spin quantum number, are -1/2 or +1/2. There's only 2 values, so for every single one, it'll either be its fourth quantum number will either be a +1/2 or a -1/2, and that is the only 2 possibilities for this. So let's recap. There's 4 quantum numbers. The principal quantum number, or the first quantum number, you can think of that as the energy level, and it's going to be whole numbers, starting at 1, going up to infinity, however high the energy is. Then there is another aspect of the place where the electron is around the nucleus called the shape, or the secondary quantum number, which we refer to as the shape. It has a symbol italicized lowercase l. And its possible values go from 0 up to whatever n is -1. The third quantum number, the magnetic quantum number, you can think of as the orientation of the shape, which is on a particular energy level. And that orientation has the values, based on what L is, has the values of negative L value all the way up to positive L value. So if the L value was 0, the ML values could only ever be 0. But let's say the L value was 2, then the ML values could go from -2, -1, 0, +1, and +2. Whatever the orientation is, whatever the third quantum number is, there are going to be 2 possible fourth quantum numbers to describe the last aspect of that particular electron. And they're referred to as the electron spin, and there's going to be only one of 2 possibilities. One possibility is a +1/2, and the other possibility is -1/2. It's referred to as spin. You can sort of think of it as being either clockwise or counterclockwise. It's kind of a neat way to think of it. Not that electrons have a particular way of spinning, not that they're just like particles or anything like that, but that is an easy way to think of it. So each orientation has one of 2 spins, +1/2 or -1/2. The possible orientations are defined by the shapes, and the possible shapes are defined by the energy level, working our way all the way back up to the principal quantum number. All right, with this information, we can attempt to build what's known as a quantum tree. So we can start by saying, okay, well, let's get the rules straight. So first of all, our principal quantum number, the first quantum number, is the n value. And the n values can be any whole number. So imagine we can't be 0 because then you're not talking about any energy at all. So the first value that we could possibly have is an n value of 1. And then we could have an n value also of 2. or we could have an n value of 3. We can't have an n value of 2.5 or 3.7 or anything else. It has to be a whole number. So that's our possible first quantum number values. And then our secondary quantum number, L, is going to be based on what n is. So depending on which n you're dealing with, you may have different L values. Let me just change the color of that a little bit. So imagine that yellow. So if you have a n value of 1, the L values can only be 0 up to n minus 1. So that's 0 up to 0. So that means the only L values can be 0. But when there's a principal quantum number 2, the L values could be 0 or they could be 1. And if you have a principal quantum number 3, they could be 0, they could be 1, or they could be 2, up to whatever the n value is, minus 1. So for the different n levels, we can have different L values. So let's just connect these so we can see them. So n value 1, you have a possible L value 0. If your principal quantum number is 2, n value of 2, you have 2 possible L values, 0 and 1. If your principal quantum number is 3, the L value could be 0, 1, or 2. So that's the secondary quantum number. Now let's try getting some green here. So ML, the third quantum number, is denoting the orientation. So L is the shape, and N is the energy level. ML is the orientation. And ML is going to be based on what L is. L is a negative up to L is a positive are the possible ML values. So in the first one here, if the principal quantum number is 1, L value could be 0. Your ML values, the only possibility we have would be 0. Because negative 0, 0, and positive 0 are all just 0. Looking at the other option here with a principal quantum number of 2, there's 2 possible L values. So think of those as 2 possible shapes. There's this 0 shape and this 1 shape. If L is 0, then we know that ML must also be 0. The orientation must also be 0. But if L is 1, then we have 3 possibilities. We have negative 1, 0, and positive 1. We have those 3 possibilities. And let's mark these off here so that if this principal quantum number is 1, the only L values you could have are 0, and the only ML values would lead up to an ML value of 0. If the principal quantum number is 2, you could have 2 L values, 2 shapes, the 0 and the 1. If the shape is 0, just like before, there's only one possible orientation. Now this 0 here and this 0 here, they are the same type of orientation, but this one's under energy level 1, and this one here is under energy level 2. So there's 2 different spots that happen to have the same orientation, as well as the same shape, but 2 different energy levels. If the energy level is number 2, it also has the option of having this 1 in there as well, because remember it goes from 0 up to n minus 1, so from 0 to 1. And if the shape is 1, then there are 3 possible ML values, or 3 possible orientations within that particular shape. There's the negative 1 orientation, the 0 orientation, and the positive 1 orientation. All right, so let's fill this one in as well. This one here, if the energy level principal quantum number is 3, it has 3 possible shapes to that energy level, the 0 shape, the 1 shape, and the 2 shape, based on the fact that L is equal to n, from 0 to n minus 1. So just like the one before it, there's going to be 3 possible orientations for this 1, and this 2, this is where you start wishing you had a longer page. This 2 is going to have 5 possible orientations, and I don't think I'm going to be able to fit those all in there, but 5 possible orientations. Let's get our green back here. So this energy level 3, if it happens to be shape 0, it only has the 0 orientation. If it's energy level 3, it could also have a shape 1, which happens to have 3 different orientations, -1, 0, and +1. And if it's energy level 3, the third type of shape that it could have is 2 here. So let me just bring this up here. It could have -2, -1, 0, right off the screen, +1, and +2. 5 possible orientations. Now that's only the first 3 quantum numbers. The last one, let's do this in purple, is the MS one. And if you got those 3, the MS one's easy. For every orientation that there is, there's going to be 2 possible spins. So this orientation here, this 0 orientation, has 1 spin or another spin. And remember, there are only going to be 2 possibilities. We call one of them a -1/2 spin, and we call the other one a +1/2 spin. And for every single one of these orientations across the board here, each one of them is going to have 2 of those possible spins. So that this orientation is going to have 2, this orientation is going to have 2, and as you get going, you're going to want more and more space widthwise, because each of these orientations is going to have these 2 spins here. So it'll have either a -1/2 spin or a +1/2 spin for every single one of these across the board. So by the time you get over to energy level 3, shape 2, it has 5 different orientations. Each one of them would have 2 spins. One of them would be the 1/2 positive, and one of them would be the 1/2 negative. It doesn't matter which one's which, but there would be 2 possibilities for each one. So this ends up, if we draw in, let's get the other 2 in here. So you have 2. I won't write the 1/2 positive, 1/2 negative for each one, but there we go. If I were to write in the 1/2 positive, 1/2 negative for each one, we'd see them across the top here. So there we go. We've got our 4 quantum numbers denoting the place of the electron around an atom. And we can remember that there is the principal quantum number, which is going to be a whole number. There is the secondary quantum number, which is based on what the principal quantum number is. The orientation, or the third quantum number, which is based on what the second quantum number is. And then for every orientation that there is, there's 2 possible values for the 4th quantum number. It can either be a -1/2 or a +1/2. And we want to think of these as being descriptions about an electron around an atom. And if we start to look at this, what we can see is, let me just draw in the circles. I won't bother writing the halves in. 1, 2, 3, 4. Let me get that 5, and then finally 6 here. And I'll leave those for now. But there would be 2 for this orientation, 2 for that one, and 2 for that one, so a total of 6. And there's 2 orientations here, 2 spins for this orientation here. So what we can start to see is the connection between the quantum numbers and the periodic table. If these numbers describe the information of the location of an electron around an atom, or we can think of it as a spot where you might be able to find an electron within the first energy level, there is going to be 2 spots where you can place electrons. You can put an electron here that would have this spin, it would have this orientation, it would have this shape, and it would be in this energy level. Or you could have the other spin with the same orientation in the same shape on the same energy level. But that's it. There's only 2 possible values, and then that energy level is full. Think about where you've seen this before. On the second energy level, when the principal quantum number is 2, there's 2 possible shapes. The first one has 1 orientation, which has 2 spots, and the second shape has 3 orientations with a total of 6 spots. 2 and 6 is 8, and you've seen that before where we've had the second energy level having 8 spots where electrons could be placed. So once you understand how these quantum trees are built, then you can start putting it together in your head as to how the periodic table shows you where electrons are placed around the nucleus. In the first energy level, there can be 2 electrons placed, and then that energy level is full. So if you had something that had 3 electrons in it, you could put 2 there, but its final valence electron would have to go in the next energy level up. That energy level could hold up to 8 more electrons. A group of 2 that is under the first shape, and then a group of 6 which is under the second shape. And take a look at this. Take a look at your periodic table. See if you can figure out the connections between the quantum trees based on the quantum numbers and the arrangement of the periodic table.